Hey, it's Tim the Tutor with Free Test Prep Online, and in this video we're going to go over stereochemistry, and in particular, we're going to cover the stereochemistry of molecules with 0, 1, or multiple stereogenic centers. What is a stereogenic center? A stereogenic center is an atom, usually carbon in organic chemistry, with 4 unique groups connected to it. So rather than go over that definition more, it's probably best to just illustrate with some examples what a stereogenic center is. So if we look at these molecules here, you'll see that hopefully the molecules on the left-hand side do not have any atoms that are stereogenic centers. You may be wondering what's wrong with the atom right here. We know that it's a skeletal structure, so we know that there should be a hydrogen bonded here. But if we actually look at the connections of this central carbon here, I have a methyl group, a methyl group, an ethyl group, and a hydrogen. So because I have 2 methyl groups bonded to that same carbon, it is not a stereogenic center because we need 4 unique groups. If we look at the bottom left molecule, we have the same idea. Don't let the wedge and the dash fool you. Just because we draw a wedge and a dash on a molecule does not mean we have a stereogenic center. The problem with this is that, again, on that central carbon, we have 2 methyl groups, and the presence of those 2 methyl groups indicates that we do not have a stereogenic center. Up here, we may be considering the carbon here. However, there's a carbon-carbon double bond, so that implies that there's only 3 groups here. So that is not a stereogenic center either. Then we can look at the one below that. And this one gets a lot of students mixed up because it very much looks like we have a stereogenic center on this carbon. But if we actually break down what that carbon's bonded to, we have a methyl group, an ethyl group, a chlorine, and a second ethyl group. So sometimes that dash makes people think it's a stereogenic center, especially because it looks a little bit different than the other ethyl group, which doesn't have a dash on it. So it kind of tricks people into thinking, yes, there's a stereogenic center, but when we actually analyze it, we have no stereogenic center. So these 4 molecules on the left here have no stereogenic centers. The 4 molecules on the right, on the other hand, all have stereogenic centers. I'm going to put a box around them and we can see why. So this central carbon has a hydrogen, an OH group, a CH3 group, and a CH2CH3 group. So a methyl, an ethyl, a hydroxide, and a hydrogen. So that is 4 unique groups, so that is a stereogenic center. If we look at the one below that, we have a stereogenic center in this position. And again, we have to draw in the hydrogen that isn't shown. And since we have an OH on a wedge, we can just automatically assume, since there's not a dash drawn, that we can put the hydrogen on a dash. So in this case, we have a hydroxide, a hydrogen, a methyl group, and an ethyl group. In the top right, we have something very similar. We have a hydroxide, a methyl group, a fluorine, and we have the hydrogen that is not shown. So there's our 4 groups on this central carbon. And then on the bottom right, again, we have a bromine, an undrawn hydrogen, a methyl group, and an ethyl group. So all 4 of these have a stereogenic center. Now that we've reviewed what a stereogenic center is, let's take a look at a couple different examples. We're going to start with molecules with 0 stereogenic centers. You can see in this drawing here that I have 2 methyl groups on the central carbon, meaning that we do not have a stereogenic center. Let's discuss some ways to describe a molecule without any stereogenic centers. So I'm going to draw the mirror image of this molecule that you can see right here. The mirror image drawn is both superimposable and identical to the original molecule. What I mean by that is you can rotate the drawn molecule to get all 4 of its groups to line up with the other molecule. In this example, it would be a lot easier to use a molecular 3D modeling kit to show you how this is possible. But essentially what we're doing here is we'd be knocking over the molecule, we'd be tilting it so that that top group ends up becoming one of the legs of the tripod, and the CH3 on the bottom right ends up standing straight up. That would actually make it so both the methyls line up, the hydrogen is going backwards, and the OH is still going forwards, lining all 4 groups up. On the next row, you can see that the molecule on the bottom left is exactly the same as the molecule on the top left. Here what I'm showing is that, again, I have the same 4 groups and no stereogenic centers on that bottom right molecule, but these 2 molecules are also identical. They're just rotated by 60 degrees from that top methyl group. You can see in this example as well, it's just rotated in 60 degrees in the opposite direction from that group. So in other words, all of these are the same molecule. Another term that we use to describe a molecule with 0 stereogenic centers is that it is achiral. Chirality refers to handedness, such as left-handed and right-handed versions of the molecule. Since the mirror image of a molecule with 0 stereogenic centers is superimposable and identical, that means there's not a left and right-hand version, it's just one version. So that means the molecule is going to be achiral. In addition, it means the molecule has no enantiomer. An enantiomer, as we'll go into more detail later on in this video, is a molecule that's mirror image is non-superimposable. Here, the mirror images are always superimposable. And last, we would say that a molecule with no stereogenic centers is optically inactive. In other words, it does not rotate plane polarized light. Next, let's talk about molecules with exactly 1 stereogenic center. Depicted here are 2 molecules that have the same 4 connections. They are isomers of each other. They are not, in fact, identical. They both have 1 stereogenic center because they have a methyl group, an ethyl group, a hydrogen, and a hydroxide each. So how do we describe these 2 molecules that both have exactly 1 stereogenic center? Well, if we look at these, you can see that they're actually mirror images. But we already discussed that they are not identical and they're not superimposable. Why is this true? Well, if you try to rotate this molecule on the right, any direction at all, try to knock it over, flip it, do whatever, you can never get all 4 of its groups to line up with the 4 groups on the other molecule. If you want to prove this to yourself, feel free to build this with a molecular modeling kit. We call one of these the S isomer and the other one the R isomer. We'll go over these absolute configurations in a different video. But this refers to the handedness of each one of the molecules. We can consider one of them to be the left hand and the other to be the right hand version. In other words, we say that these molecules are chiral. Molecules with 1 stereogenic center always have an enantiomer. However, they do not have any diastereomers. We'll go over what a diastereomer is in another slide. Lastly, a molecule with a 1 stereogenic center is always optically active, meaning it rotates plane polarized light. Let's review a little bit more about what an enantiomer is. The 2 molecules depicted here are enantiomers of each other. We already mentioned that an enantiomer is a non-superimposable mirror image. However, that's only one way to identify an enantiomer. The other way we can do it is to recognize that an enantiomer is a type of stereoisomer where all the stereogenic centers have the opposite absolute configuration, meaning R or S, which again we'll cover in a different video. Enantiomers are interesting because even though they're different molecules, they have the same melting point and the same boiling point. That makes it pretty much impossible to separate them using physical separation techniques in a lab, such as distillation. The last key point about enantiomers is that they rotate plane polarized light by the same exact angle, but in opposite directions. Once we get beyond molecules with only 1 stereogenic center, things can get a little trickier because there are 3 different possibilities. The first possibility is enantiomers. If we look at these 2 molecules below, how would we say that they're related to each other? Well, if you look at them, both of them have 2 stereogenic centers, and they have the same connections around each of the stereogenic centers. They're also mirror images of each other. However, if we really take a careful look, we would say that they are definitely non-superimposable mirror images. This makes them enantiomers. Now, how do we know they're non-superimposable? Well, there's no way that we can flip or rotate or manipulate the molecule on the right to look like the molecule on the left. Sometimes students think, well, what if we flip it from left to right 180 degrees? So when you actually do this, So when you flip that top right molecule 180 degrees left to right, you get the bottom right molecule. And whenever you do a 180 degree flip, any atom that was facing backwards, which means it was on a dash, is now going to be facing forwards on a wedge, and vice versa. And when you compare that to the original molecule, you can clearly see that the two stereocenters do not line up with each other and are, in fact, opposite in configuration. Of course, enantiomers are not the only possibility when you have molecules with two or more stereogenic centers. Another possibility is that you have a meso compound. Let's look at the two molecules depicted here. How are they related to each other? Well, notice they have the same exact molecular formula, and they actually have the same exact connections at each of their two stereogenic centers. They're also mirror images of each other. So, one might look at this at first glance and be like, oh, they're mirror images. They must be enantiomers. However, if you look carefully, I literally drew the same exact molecule on the left and on the right. They are also mirror images, which actually means that they are superimposable mirror images. That means they're identical, not enantiomers. The name for a molecule with two or more stereogenic centers that has an identical mirror image, that is, it has no enantiomer, is a meso compound. Let's look at these two molecules that I've drawn. You can recognize a meso compound by identifying a plane of symmetry within the molecule itself. So with these two molecules in the bottom left, it's not immediately obvious that they are, in fact, the same molecule, and therefore it's a meso compound, because sometimes you need to rotate a bond before a plane of symmetry becomes obvious. So if you were to flip the bond 180 degrees, that's going to put the CH2OH, the Cl, and the Br in the same position as they look on the right, and therefore we have a plane of symmetry in the molecule itself. Meso compounds, despite having stereogenic centers, are achiral and optically inactive. Now we're going to cover our final possibility for molecules with two or more stereogenic centers, and that is we have diastereomers. So let's look at these two molecules depicted here and evaluate how they are related to each other. Notice that these two molecules both have two stereogenic centers, the same chemical formula, and the same connections at both of those stereogenic centers. But also notice that at those connections they have different spatial orientations. So if you look at them, we cannot draw a mirror plane between them. They are neither mirror images nor are they superimposable. When you flip the molecule on the top right 180 degrees from left to right, you get the bottom right molecule. And again, any atom that was facing backwards on a dash is now going to be facing forwards on a wedge and vice versa. When compared to the original molecule, you can clearly see that only one of the two stereogenic centers has the same configuration in both molecules. Stereoisomers that have two or more stereogenic centers, where at least one, but not all, of the stereogenic centers have opposite configurations, are called diastereomers. Diastereomers, unlike enantiomers, have different melting points and boiling points, and when they're chiral, so meso compounds, despite being achiral, they still have chiral diastereomers. They rotate plane polarized light at different angles. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.